Uh, Students, good afternoon. Am I audible? One of you can unmute and respond. Maheshwar, am I audible?
Yes, sir.
Okay, fine. So, I am Richard and I will be handling your digital electronic circuits. Okay, and just before we start, okay, what we will do is we will just look at the uh, syllabus, okay, and we will try and understand as to exactly that we are going to learn. So I'm just putting up the syllabus for you all. Just give me a moment. Are you all able to see the screen? Now is it visible? You can use the chat box as well. Okay, that's great since I've got a confirmation. Uh, Now this is going to be your subject, okay, 19 AC 33, which is nothing but your digital electronic circuits. Now I think most of you have, you know, studied basic electronics. So this subject is going to be an extension of your basic electronics, okay, especially the digital part. So once you are into this subject, okay, the objectives are that you should be able to understand the fundamental concepts of logic design. That's going to be number one. Now logic design, when I say, it's going to be your digital designing of a circuit, okay, the digital part. Then how we simplify Boolean expressions. We might have some complex Boolean expressions. So how do we simplify using standard methods? So now when I say standard methods, it's going to be your K-map, which is nothing but your Karnoff map, or it could be your Quinn-McCluskey method. For your syllabus point of view, we will be studying K-maps. Okay. Then you'll be able to demonstrate knowledge simplification by designing combinational logic circuits. So how will you be able to design? Based on certain equations. and equations are reduced using your Boolean expressions. Now, not only having an expression, but we should also get them simplified. Okay, so simplification also happens. Then you will have something called flip-flops. Now, what is a flip-flop? Can one of you respond? What is a flip-flop? I think you have studied in your basic electronics. What's a flip-flop? I want my class to be interactive. Okay, and you can unmute yourself and you can respond. Lavanya, anyone who wants to respond? What's a flip-flop? Anyone can respond. Yes, what's a flip-flop? Are you able to hear me? Yes, I'm audible, isn't it? Mamta, can you respond?
Sir,
Yes, I am. Go on.
sir, flip-flops are actually like meant for temporary storage of data, no, sir?
Okay. Yes, you are almost there.
And they are also somewhat similar to latches.
Okay. Fine, Sayan. Now, in continuation to what one of your friend has responded, okay, flip-flops are nothing but your basic building block of a memory. Okay, so it can be a temporary memory or it can be a permanent memory. It can be erasable memory, programmable memory. In general, flip-flops is a basic building block of memory, just like how your cell, okay, just like how a body is made up of a cell which is nothing but the most basic building block. Similarly, your memory has a basic element and that is called a flip-flop. Okay, fine. And you will be able to examine the significance of state machines. State machines are nothing but, you know, you'll be able to find out, you know, what is going to be the state of your machine in another next state, in the present state. Okay, so that is what is called a state machine. Then you'll be able to design combinational and sequential. Now, can someone tell me the difference between these two? I think extensively you would have studied this, the differences between combinational and sequential circuits, right? So can someone respond? I want you all to be a part of my discussion. What is the difference between combinational and sequential circuit? Anybody can unmute and respond.
Sir, sequential circuits depend upon the previous output of
Okay,
another circuit,
okay,
whereas combinational depends only upon the present state.
exactly. So if it's knowing what is the previous state, it means it's having a certain amount of memory involved, isn't it? Right? So this is the difference between good sign. Thank you. This is the difference between your combinational and sequential circuits. Okay, combinational works on whatever is the present combination, whatever you give to them as your inputs. It's accordingly you're going to get an output. For example, let us take AND gate. So in your AND gate, you have two inputs and one output. So operation is nothing but multiplication, right? So AND gate doesn't remember what was the previous output. So if your circuit is able to remember what was its previous output, then it's going to be your sequential circuits. So circuits involving memories are called sequential circuits. So I hope we are clear with what we are going to accomplish once we are done studying digital electronic circuits. Okay. So to start off, we are going to take up module 1. Okay. So module 1 is nothing but your principles of combinational logic, and later on we will move on to module 2, 3, 4, and 5. Okay. So in module 1 you have something called binary logic. Okay. So I think many of you would have been aware of the term binary. Today's world, that whatever you see, the digital world that we see, is actually dependent only on two values, which is nothing but 0 and 1. Okay, so that is your binary logic. Anything that you see, okay, it's only dependent on the binary value. Next, you have pass gates, logic gates, okay, CMOS, De Morgan's theorem. I think this term is very much familiar to all of you. Then K maps, we will have some equations. Okay, then we will learn few techniques. MEV technique, map entered variable technique. Then how do we realize certain functions using MOS logic? So all this we will understand using your module 1. Okay, so this subject is very interesting subject. Okay, perhaps you need a little bit of attention to detail. So when I say attention to detail, when I'm explaining few things, you have to really concentrate. It's only then you will find it to be uh, interesting, and you can concentrate on what we are doing. Okay, fine. Now, yeah. So this is what I wanted to discuss about your syllabus. Now, I think all of you have joined Google Classroom, isn't it? So what I will be doing is I will be posting the attendance link there after the class. Okay, so you can click on the link and mention your name, USN. Okay, those details. I think by now all of you would have received your USN, isn't it? So you can click on the link. Okay, and you can actually give the attendance. Kamala, do you have a question? I see your hand is raised. Kamal, sorry. Kamal Pola, do you have a question?
Yes.
Yes. Any question? Please go on. Yeah.
No, sir, no, sir,
No
no questions.
question? Fine, fine. Because I saw your hand raised, so I thought you wanted to ask a question. And meantime, whenever I'm explaining anything, if in case you guys have any doubt, you can always feel free to, raise your hand. Okay. You have an option here in WebEx. Okay, where you can actually raise your hand. I will get to know, and accordingly we can interact. Okay, and we can try and understand as to what is your doubt, and we will try to solve it. Okay, fine. So this is about your your syllabus. Okay, I do not want to go much deep into it as today it's the first class for us. And tomorrow morning 9 o'clock also I'm planning to take an extra class because today we had two classes, so I couldn't make it because we had examination duty. Okay, so tomorrow morning I'll be taking up another class for you at about 9. Anyway, I will be informing you via WhatsApp group. Okay, fine. So let us get started. Now what I want you to do is I want you all to write down, okay, few important points, whatever is told, so that it will be easy for you to answer my questions in the next class. Okay. Now, is this visible to all of you? Whatever I have written here, one of you can unmute and respond. Is it visible? Okay, fine. Science says yes.
Yes, sir.
Yes. So this is the module one. As I told you, we are going to start off with module one, which is nothing but principles of combinational logic. So first, what we will do is we will only study your binary logic functions, and then we will see what is the definition of combinational logic. Okay, then we can see how key maps can be used for 3, 4, and 5 variables. Of course, Queen McCluskey we will not be discussing for your syllabus. It's revised and we will not taking it up. And then we will be having map entered variables. So this is our agenda for the class. So starting off with the logic functions. So I think you all are very much aware of this, basic functions, right? Your and, or, not, NAND, nor, exclusive or, exclusive nor, right? And I want you all to have a separate notebook for this subject, so that whatever notes, whatever thing that I am projecting, I want you to make a quick notes. Of course, I will be sharing it, but only at the end. Okay, once I finish, it's only then that I will be sending it to you. But till then, for your reference, you will have to make your own notes. Okay, and at the end, once I finish the module, I will I will anyways be sending my own notes to you all. Is that fine with you all? You can use the chat box also to respond. Okay, so please write down it as module 1, principles of combinational logic. So I hope all of you have your notebooks. Okay, so just write down module 1, principles of combinational logic. You don't have to write these things, okay, which I have written at the bottom. Just write module 1, principles of combinational logic. Under that, okay, you can put it as binary logic functions and make note of all these. Now during the session, okay, I might randomly ask anyone to show whatever you have written. Okay, you'll have to turn on the video and show me your notes as to what all you have written. Okay, so please start writing, so that randomly when I call out your name, you should be able to show out as to what all you have written down. So if you're done, we can I proceed? Can I proceed? So these are going to be your basic logical functions, and deals with multiplication or deals with addition. Not is nothing but your inversion, your negation. Okay. Then your NAND is nothing but AND plus your NOT gate, OR plus NOT gate. Okay. Then exclusive OR. These are special logical functions, XOR and XNOR. So we will see them one by one as to what they are. So this is the symbol. I think all of you are very much aware of the symbol. X, Y, and Z. X, Y are your inputs, Z is your output. Okay. Then this is going to be a truth table. And how do we represent it? Z is nothing but multiplied with X and Y. Sometimes we use the star symbol. Sometimes we just write it in brackets, X, Y. If in case in the exam, if they ask you to represent using IEEE logic symbol, then you can use this. So this is your IEEE logic symbol. So IEEE is nothing but a standard. Okay, it's a standard, just like how you have Wi-Fi as a standard, like how you have 4G as a standard, 3G as a standard. So all these standards are regularized using with the help of IEEE body. Now look at the truth table. I know all of you are very much aware with this, the operation of AND, but still I will just go through it for the benefit of everyone. 0 0 0 1 1 0 1 1. So this is going to be our combination of 2 bits, 2 raised to 2, which is 4. So I have 4 combinations, 1 2 3 4. So I can pair it up with 0 and 0. The next combination 0 1, I can flip the combination, so it becomes 1 0, or I can have X as 1 and Y also as 1. So here you should understand, since it's a multiplication process, wherever there is a 0, your answer is obviously going to be a 0. 0 0, 0 into 1 0, 1 into 0 0. So this is the only case where I'm getting the high value, because both the inputs are high. Okay, fine. So now this is with respect to your OR gate. So you have the symbol, you have the truth table, you have the equation, and you have the IEEE standard symbol as well towards your extreme right hand side.
So can you show the AND gate again?
And you want me to go back? Okay. Now keep in mind whatever we discuss, okay, just make sure that you revise them every day, because as we keep proceeding, the concepts keeps building, and you shouldn't be confused once the concepts are plenty. So it's always nice to revise then and there, that particular day, same day itself. So it's going to be beneficial for you. So I hope you all know that there's going to be assignments, there's going to be quiz. Okay, so all these are components of your CIE, continuous internal evaluation. So marks will be allotted accordingly. So you have to take these things seriously and work on it. Can I move on?
Sir.
Okay. So these combinations are going to be the same, okay, 0, 0 to 1, 1. Only the values at the output z is going to change. So here we are using addition operation. Values of x are added with values of y. If you see this AND gate and OR gate, it's totally reversed, right? Here you have 0, 111, there 0, 0, 0, 1, right? So because it's multiplication and addition. Similarly, your NOT gate here, since it's only 1 bit, so how many combinations will I have? Only 2, 0 and 1. So if my input is 0, my output is going to be 1. Similarly, 1, 0. How do I represent it using my equation? Whatever is the value z, okay, z is equal to z bar. Okay. Sometimes we use z bar, sometimes z dash. So you see a bubble here. Bubble indicates inversion of input value. So you have x and the value is inverted. Also, students, for your information, okay, I will be uploading this video as well. Okay, so I will be sharing you the link, and accordingly, okay, because what we have to do is within this 1 month, okay, we'll have to cover a lot of concepts. Um, we'll have to go ahead with quiz. So many things are there. So what we will do is, since I'll be uploading this video, it will be easy for you to pause and take down the notes as well. So is that idea fine with you guys? So since we'll have the video, you can pause and you can utilize for writing your notes. Is that okay? One of you, I need your response. Okay. Thank you, Geetanjali. Fine. So this is our OR function. Okay, this is a representation and the standard IEEE symbol as well. So wherever you see a bubble, bubble represents the inversion. Input is inverted and then it comes as output. So inversion is nothing but the reverse value. 0 is 1 and 1 becomes 0. Now if you see for NAND gate, the symbol is AND plus a bubble, right? So if you see AND, if you just put a bubble here, this becomes NAND. Without the bubble, it's an AND. Okay. So here, whatever values that you see, okay, 0, 0, okay, 0, 0 should be actually multiplied, okay, so it is 0, and at the end negated. So 0 0 is 0 and inversion is nothing but 1. Okay. Sign, I will be uploading the PDF, okay, once we are done with the module. Okay, so I will complete the module. Module wise, I will send you the notes. I will upload in the classroom. Video also, what I will be doing is lecture by lecture, I will upload it so that it will be easy for you guys to go through it and also take down notes if in case you were not able to complete during my lecture. Similarly, you take the second case here, 0 1. So when I multiply 0 1, I should be getting 0. I at the final I negate it, so it becomes 1. So this is pretty much clear to all of you, I feel. X y multiplication, and I'm using the negation here. Okay, bar, x y bar, nor. So it's a combination of OR gate with a bubble, and the equation is going to be x plus y. Suppose I don't use this, it's just going to be an OR gate. So since I'm using this dash, okay, it's going to be a NOR gate, and I'm using a bar here, which is nothing but negating whatever you are adding. So that's a NOR gate. So how do we do it? How do we get the values? 0 plus 1 is actually 1, but I'm negating it. So 1 is becoming 0. Okay. Similarly here you see 1 0. I should be getting 1. But then since we are negating, so it becomes 0. Similarly, these special logic gates, which is nothing but your XOR and XNOR. XOR has a very special application in the field of digital electronics. It is used like a comparator. How can we say that it's used as a comparator? Whenever the values are same, okay, the value is 0. Harshit, you have a question? Harshit? Um, Not audible. You can use the chat option.
Yes, sir. It's
You're not audible. You can barely
by
hear
miss.
you.
It's arranged.
Sorry, Harsha? Yeah, yeah, go on. Can you put it up in the chat? Okay, that's fine. No problem, Harsha. So this, as I was mentioning, XOR has special application in the field of electronics. So we use this as a comparator. Okay, so how is it as a comparator? 0 0 can give me 0, 0 1 gives me 1. So we can actually make a conclusion here stating that whenever the values are same, the output is 0. Values of inputs are same, 1 and 1, the output is 0. Whenever the values are different, 0 1 1 0, the values are high. So in this way I can actually check if I've got the same values or different values at my input side. So it can act as a comparator. Okay, so the the equation is going to be x plus, right? So plus is going to be circled. Similarly, x nor. So x or, I put a bubble here, becomes x nor. Okay. Here, if it is same, it's high. Different, 0. Just the opposite of this. 0, 1, 1, 0. Here you have 1, 0, 0, 1. Compare both of these values. You'll be able to find out that both are reverse to each other. So there are two ways to represent this. Either you can represent it with x, a dot, the circle, or you can just complement it, using the bar. X XOR with y, so you can use a bar. Okay, so I hope these concepts are clear. So what did we study? We studied the gates, right? We understood that binary logic, any logic can be implemented using these basic gates, okay, and or not. Your NAND and NOR is called universal gate, okay, because using NAND and NOR we can implement any function. Any function can be implemented, either addition or multiplication, whatever can be done using NAND and NOR. So NAND and NOR are called universal gates, and these are special purpose gates, XOR and XOR. So we have seen the symbol, we have seen the truth table, how we represent, and we have seen the IEEE standard symbols as well. So this can be a question for you in your internals as to write a note on the logic gates. So this is going to be your answer. You're going to put the symbol, you're going to tell what is the truth table, how it's represented using equation, and what is the standard format. So based on your marks, you decide how you're going to write your answer. Suppose I ask it for 5 marks, or suppose say I ask it only for 5 marks, then you can just put the symbols and say this is OR gate, NOT gate. Suppose I ask it for 10 marks, then you can include your truth table, equations, and all this stuff. Okay. So based on the marks, you can actually decide. Fine. So is there any doubts so far? Am I going too fast, too slow? You can give me your feedback so that we can accordingly match up for the next class. Yes, is it fine? And one more thing I would like to tell you all is, if in case the call gets disconnected in 50 minutes, okay, normally the duration for this is 50 minutes. If in case it gets disconnected, then you can always join back using the same link. Okay, I hope 50 minutes is more than sufficient, and we will use the last 10 minutes for our attendance and any other doubt clearing sessions. Then we can join back. Fine. Now, talking about the laws of Boolean algebra. So I think you all know that there are three major laws. Okay, there are three major laws. Is it someone talking? Is it someone having a query? Kamal, you have a doubt? Okay. So these are the three major laws of Boolean algebra. You have commutative law, associative law, and distributive law. Okay. You would have seen this laws previously, but anyway, I will have a recap of these laws. So commutative law says a plus b is equal to b plus a. So which means, let us take a number, for example, take a is 2 and b is 5, okay, or let's take b is 3. So if I do 2 plus 3, which is actually 5, is also equal to 3 plus 2, which also gives us 5. Now let us take the same values, 2 into 3, it gives me 6, or 3 into 2, it also gives me 6. So this is nothing but your commutative law. The next one that you can see is your associative law. So here we not only add values, but then we also use brackets. Okay, we also use brackets. So if I'm using a plus and then I group b and c together, I get a certain value. Okay, let us say 2 plus 3 plus say 1. Okay, so 2, 3, so gives me 5 plus 1, 6 is also equal to 2, 3 plus 1, right? So this is nothing but your associative law. Fine. And your distributive law, okay, your distributive law states that here we are not only using adding symbol, we are also using your bracket, and we are also multiplying. In the first one we only added, okay, a plus b. In the associative law we are using grouping, but in distributive law we are also grouping, we are adding, and we are also multiplying them. So a into b plus c is equal to ab plus ac. I think you all are very much familiar with this, right? So this is your distributive law. So these are some of the basic rules of Boolean algebra. Okay, so we will be using this very frequently, and this is going to be very important for our discussion. A plus 0 is a because nothing is getting added to a. The value of a is not getting changed, right? So it gives me the same value if I'm adding it with 0. Similarly, you have a plus 1. So nothing can be more than 1, right? Either if a is 0 or a is 1, I will always get 1 because 1 is already here, right? Anything added with the same value gives me the same value. 0 plus 0 gives me 0, 1 plus 1 gives me 1. Okay, so you can actually substitute values and check. For a, you give a certain value and check. So any variable, okay, added with its complement gives me 0, gives me 1. So let us take a as 0. So 0 plus 0 bar is nothing but 1. 0 plus 1 is 1. Anything multiplied with 0 gives me 0. Multiplied with 1, okay, gives me the same value here. Why is it dependent on this value? Because if a is 0, the value changes to 0. If a is 1, it's going to be 1. So ultimately the value is very much dependent on a. Similarly, a into a is equal to a, and then your a into a bar gives me 0 because we have two complemented values, 1 and 0. So I should obviously get a 0. Similarly, if I use a double bar here, okay, a double bar, so that should give me a. Then a plus ab gives me a, okay. A plus a bar b gives me a plus b. So this is just like you can take a in the bracket, take 1 plus, okay, or you can take yeah, you can do that. So this gives you a plus b. Then when you multiply them, a plus b into a plus c. So try and multiply them. Ultimately, when you use the Boolean algebra, you will be getting the final value a plus bc. So we will stop here. Okay, we will stop here as of now, and I will be posting the attendance in the Google Classroom. Okay, I want you all to give in your attendance. Next class we will study about De Morgan's theorem. Okay, so De Morgan's theorem is very simple. A b bar, when it's multiplied and you split them, it becomes addition including individual bar. And similarly here, if it's addition and having a bar, individual multiplication with bar. Okay, so this is your De Morgan's theorem. Tomorrow we will see what is a combinational logic. So any doubts? Any doubts you have so far, whatever concepts that we have discussed? Okay then, so we will end this session, and we will get back to Google Classroom. Okay, thank you.